All right, you may remember we used this little apparatus last chapter when we were talking about solutions. And what were we using it for? What are I trying to illustrate for you? Emily.
What? What?
I asked a question.
Yeah, what are you trying to illustrate for us? Demonstrate?
That's my question.
Alright. Do you want the answer?
Yeah?
Okay. How to demonstrate something?
No, she's not listening because she was texting, but that's okay.
Oh, I really wasn't texting. I was making this line on my paper.
Well, it was important anyway, as long as it was important. Lines on the paper, texting. Okay. All right, anyway, as Emily so astutely noticed, that I'm not talking about that anymore. I'm not talking about titration right now. I'm talking about something we did last chapter with this light bulb. What did we use it for? Electrolytes, right. And I actually tested this guy here, but I told you I was going to come back to him, I think, at the time, and I'm going to come back to him right now. I tested hydrochloric acid. A lot of times you guys think, well, a difference between a strong and a weak acid, you probably have different ideas. Okay, what makes something a strong acid, what makes something a weak acid, all right? Strong acids obviously are ones that are going to burn you badly. You would think that. But you might have thought, from what we did the other day, that, like a guy that has 2 or 3, like well, that's a bad color. Like H3PO4, phosphoric acid, would be stronger than HCl. That's what you might think, based on what I told you about mono versus diprotic acid, right? H3PO4, HCl, this guy's going to be stronger. He's got 3 times as many H's, but he's not. Strength of acid is not determined by how many H's he has. All right? The concentration is affected by that. I have to calculate the normality. But it's not the strength. The strength of the acid has to do with something else. It has to do with how well it dissolves in water and reacts to form hydronium ions or hydroxide ions. Okay? So when I put some hydrochloric acid, which is going to be my first example on my notes, we see that this guy gives me a very bright light bulb, right? Okay? And I'm going to wash that off so it doesn't ruin the light bulb. But you saw how bright that was. Okay? Whereas, and I'm going to test this one now so I can move it out of the way, when I test the vinegar, all right, in this, same thing. Oh, by the way, I better wash that off first. Because watch, just the amount of acid left on those wires, see, it still lights the light bulb a little bit. Just wash that off first. But now when I test the vinegar, which is also an acid, not so much. Just barely lights that light bulb. If you turn the light off, you can probably see even better. Okay, see it? Okay. So turn it back on. So I have to explain to you the difference, and it has to do with the electrolyte, same thing we talked about before, how well it dissolves in water to form ions. The specific ions we're talking about, however, are hydronium or hydroxide ions. So let's talk about that now. Okay, strength of acids. Oops. Strength of acids and bases. Acid-base strength. I'm going to come back and use this again for some other things I want to test as well. How do you tell a strong acid from a weak acid? Well, it's not about how many H's he has, as I just made out to you. It's not even about how dangerous it is necessarily. Acetic acids, concentrated acetic acid, is pretty nasty stuff. You really wouldn't want to get that on you or inhale any of it. It's about the degree of ionization or dissociation in water. That's what it's all about. How much it breaks up in water. Now, it turns out that strong acids and strong bases, they break up completely in solution. Okay? And you saw that. When I put that light bulb, I put that solution across the wires to make that light bulb light, hydrochloric acid, which is a strong acid, made that light bulb light very brightly, whereas you'll see the acetic acid did not. Okay? So strong acids or bases break up completely into either hydronium or hydroxide ions in solution. When I say completely, I mean 100%. Whatever I put in there, that's how much I get of hydronium or hydroxide ions. It actually works from a stoichiometric standpoint even. Stoichiometry, remember that? If I know the concentration of the reactants, I can predict the concentration of the products. So let's use a little stoichiometry here. Let's look at this equation, which, I could talk about this equation a lot of different ways. All of this stuff in this chapter eventually comes together. Matter of fact, tomorrow's worksheet we're going to do, which I was thinking about possibly even doing today, but I don't think I want to do that. I think we're going to save it for tomorrow. I have time to do a few more examples and practice today. Plus, you guys did not get time to work on these. Remember, we went right to the lab yesterday, so I want to give you some time to work on those. I'll be done probably in about 15 minutes. It's in a long class, but I figured I'd give you time for both of those things. Because tomorrow, we're going to have a worksheet, and it's going to be all-encompassing. It's going to have stuff on just about everything we saw in this chapter. It's going to be a pretty long worksheet, okay? So if I gave you this equation right here, right, I could talk about a lot of different things about that equation. Today, I want to talk about the fact that when I add HCl to water, it completely and utterly changes from HCl. All of the HCl becomes hydronium ions and chloride ions, 100% of it. Such that if I put in 1 molar of that, remember stoichiometry, if I had 1 molar solution of HCl, I would get 1 mole of hydronium ions and 1 mole of chloride ions. But I would get to that, 100% of it. And I'd be left with no HCl, over here. It'd be 100% of that. So I could actually predict that from a stoichiometric standpoint. But I told you that's one way I could talk about it. In that worksheet tomorrow, what are some other things I could tell you about? I could ask you to name this acid. Everybody can name that guy. He's a piece of cake. What is he? Hydrochloric acid. I could ask you, is he an Arrhenius or a Bronsted acid or base?
Is it? Bronsted.
Some say Bronsted, some say Arrhenius, and both are correct because he's a Bronsted acid because he does what Bronsted says he should do. He gives up an H. Is he an Arrhenius acid as well?
Yeah.
Because he forms hydronium ions. Exactly. So these are the different ways I could talk about this guy. If I wanted to get the normality of HCl, what would it be? Still 1, because there's 1. All of this is going to be on that worksheet tomorrow. It's going to be more of a quiz than a worksheet. Okay. All right, but today we're talking about strength. Here's the difference. Strong acids like hydrochloric acid, sulfuric acid, they break up 100%. Weak acids like, strong base. I forgot what I'm talking about. Strong bases also in the strong acid bases. They break up 100% in solution too. They don't do it the same way. They don't react with the water and form hydronium ions. They dissolve in water and form hydroxide ions. Okay, but the key to this is it's 100%. All of the sodium hydroxide I put in, I will get turned into sodium ions and hydroxide ions. So if I put in 1 mole of sodium hydroxide, I get 1 mole of hydroxide ions. Okay, 100%. That makes them a strong, and by the way, that's how a pH meter works. You guys aren't going to use pH meters this year. We've used litmus paper and different indicators to tell the pH. Next year in Chem 2, we will use a pH meter. And the pH meter is like a glass bulb, and you stick it into the solution and it tells you the pH, reads it right off of there. It does that, the same basic principle as this, kind of. Not exactly, it's a little different. But it has to do with the conductivity of the solution. It has to do with, it can measure how well it can conduct electricity, basically, with the voltage difference. And it has inside of that little glass bulb its own little solution, and it can tell how much hydronium ions are on the outside of it. All right, so it can tell the pH of the solution by measuring the conductivity, basically, of the solution, how well it conducts electricity. And a guy like this, let's test him. I told you I was going to come back to this anyway. All right, if I test sodium hydroxide, what are you going to expect to see? Here's sodium hydroxide, right? Here's my sodium hydroxide, and here it is. Now you saw what happened with my strong acid. What will we expect? Sure enough, very strong light. Okay? Again, I want to wipe it off, rinse it off quickly, because we don't want that stuff. Notice it stays on there a little bit. And as a matter of fact, I'm going to even use a little vinegar to make sure none of that stays on there too long. And then some more water. Because the sodium hydroxide, it'll definitely get rid of the base on there. I don't want it to corrode these wires that are actually in there. All right, so rinse it off good. There you have it. So sodium hydroxide, no surprise, 100%. Also, very bright light bulb. right? But when we talk about weak acids and bases, we can have a different story here. A weak acid and a weak base, these guys do not break up 100% in solution. They only partially ionize and or partially dissolve in solution. You saw that with the vinegar a little while ago. And you're going to see that with my weak base I have. Okay? My example for my weak acid is actually vinegar. Vinegar is a weird formula you don't know about. Next year when you take Chem 2, you're going to learn organic. You're going to learn why he has this crazy formula. It actually has carbons in it, and you would not draw it like this if you were drawing the organic way. But that's the way we draw it when we're running on one line, and we're talking about its acidic properties. That is vinegar. That is acetic acid. Notice what happens. And you can identify that as an acid. Even though it doesn't look like one based on its formula and the way it's written, it ends with an OH, looks like a base. Look at the equation. What's he doing in this reaction? He's donating an H. You see it? Does everybody see how he's donating an H? Right? This H at the end here is being given up to water to form hydronium ions, which makes him an acid in both senses. He's an Arrhenius acid and the Bronsted acid for donating. All right? But here's the difference. Watch this. Notice I've got arrows going both ways. Remember what it's amazing how many things, you guys can't see it now because you're in the beginning or the middle of it. But at the end of Chem 2, and certainly me, having taught both classes full all the way through, can see what you guys can't. We saw equilibrium for the first time, these kind of arrows, double arrows, when we're talking about phase changes. Then we saw them a little bit under solubility, plus solvent yields solution. Believe it or not, it also works for equations, chemical equations. And that is just like this guy can come together with that and make him, the products can also become reactants. This is a reversible reaction. It doesn't just go one way 100%. As a matter of fact, you know about how the approximate percentage this does it? About 4%. Only about 4% of the CH3COOH breaks up into hydronium ions. So here's the crazy part. If I put 1 mole of this stuff in here, I do not get 1 mole of hydronium ions. I only get about 4% of that turned into hydronium ions. And that's why when you saw me do the bottle for vinegar, the beaker for vinegar, it didn't work very well. Okay? And the same thing is going to be true if I do a weak base. And this is going to bring one more thing home to you, hopefully. The base I'm going to use is calcium hydroxide, which is lime water, basically. All right, put a little bit in there. And if I test this guy, you'll see that you just saw me do sodium hydroxide. All right, if I test this one, notice it's a lot dimmer bulb, right? You can see it, but it's not very bright. The sodium hydroxide, which is a strong base, was very bright. Let me rinse that off before I show you what I want to show you about that. Calcium hydroxide's formula, you might have thought, is going to be a stronger base. Because if you write calcium hydroxide correctly, don't do this. But if I wrote calcium hydroxide correctly, wouldn't it be CaOH2, right? Because he's a +2 and he's a -1. So you'd say, oh, he's got twice as many hydroxides. He's going to be a stronger base. But he's not. He's a weaker base than sodium hydroxide. Because sodium hydroxide breaks up 100%. Now, did you notice how much he broke up? You know how bright that light bulb was, right? The vinegar. If you remember the vinegar, was it brighter or darker, or brighter or not as bright as that? Not as bright. So what would that probably tell you about vinegar? If vinegar broke up 4% and it was a little dimmer, what do you think this guy breaks up maybe? A little bit more than that, right? Okay. And that's how a pH meter kind of works. It basically is measuring the ion, the charge, that's able to measure of the hydrogen ions, all right, that are compared to a standard, which is actually inside that bulb. Now, you're going to use that next year. You're not going to use it this year, the pH meters. But weak acids, weak bases, small percentage breaks up. Strong acids, strong bases, all of it breaks up in solution to hydronium or hydroxide ions, depending if it's an acid or a base. All right, good enough. Now, is there a way I can predict whether something's a strong acid or a strong base? or a weak acid or a weak base? The answer is yes. I mean, obviously, I could look at a chart, and in a chart in the back of your book and a chart in the back of Chem 2 book, there's something called a Ka and a Kb. It's a constant that tells you the size of that would tell you whether it's a strong or a weak and how weak or how strong it would be. However, there are some rules of thumb that you could basically go by to tell you how strong the acid or base will be. And that's what I want to show you now. Just some general ideas about if you were going to predict the acid or base strength. I want to give you those, and that's all I'm going to do. That'll be the end of it for today. Because tomorrow, or the rest of the period, you will spend doing some homework, hopefully, that you didn't already get done. So predicting acid strength, all right, I want to show you a couple of tricks. If I have a binary acid, this is the one that I think makes the most sense and you will understand the most. The other ones you kind of have to do a little bit of memorization, but this one, it should make sense, as you'll see. Binary acids, well, you know what binary acids look like. They have two, like HCl, HF, HBr. All right, well, think about it. What does an acid want to do? An acid, whatever he is, let's call it HA, whatever that next guy is, HCl, HF, wants to lose an H to something else, a lot of times to water. So the easier it is for him to lose that H, the better the acid is, right? Now let's just look within a group. Look at group 7 over there. Fluorine, chlorine, bromine, and iodine. And we'll write them in order here, okay? So we'd have HCl, HF, HCl, HBr, and HI. Who you think is going to be holding on to that H the best? Yeah. So guess what? What kind of an acid do you think he is? A weaker acid. Because what does the definition of an acid again? What does an acid want to do? He wants to get rid, he wants to lose, that's the definition. Things that lose H's and give them up are good acids. So guys like fluorine, who are very electronegative and holding on to that H, not going to be such a good acid. As I go down that group, I'm going to get better acids, right? I get better acids as I go down. Because there's going to be less electronegativity, not going to be held as tightly. All right, and that's the rule. Acid strength is inversely related to bond strength, and therefore, they're going to lose hydrogen ions more easily. So I would expect the weaker the bond, the better the acid. The lower the electronegativity difference, the closer they are together. One's not holding as tightly like fluorine is holding really tightly, not going to be as good an acid. Okay? So within a group from top to bottom, the electronegativity decreases, so the acid strength is going to increase. Now, this is a rule of thumb. It's not perfect, all right, but that's in general what's going to happen. A better way would be to actually look at constants that we're going to learn about in Chem 2 called the equilibrium constants for acids and bases, Ka, Kb. But we're not doing that right now. We're just going to do some general stuff. So again, if you have the bond strength going, HF being the strongest, HI being the weakest, if that's how the bond strength goes, what are you going to expect for the acid strength? Be the exact opposite, right? Inversely related. What might I ask you in the homework tonight? What might I ask you on that sheet tomorrow? Given these two acids, who's stronger or who's weaker? If I give you two binary ones, you'll just look at who's going to have the weaker bond, therefore who's going to be the less electronegative. Got it? You don't?
I don't know.
Well, let's do a quick example, although you're going to get ones in the homework tonight anyway. Given HBr versus, don't write this down, HI. Without looking up there. There's HBr, there's HI. HI is lower down, not held as tightly, he'll be the better acid. So the HI will be the stronger.
What about HO and HTE?
Well, again, if I say, what would you tell me? It wouldn't be H, it would be H2, but will you tell me? Who would be the better acid?
HTE.
Right. Now, not that that actually happens, because tellurium is actually more of a
Okay, but what if it's like...
Are we going to have HNA? Does that even sound right? What is H going to combine with? Guys, on the right side of the periodic table. So like H2S and H2O.
All right, then I don't have any questions.
Okay.
I was just thinking...
Now, there are other problems, though. Like maybe you were thinking, somebody was thinking about, what about the ternary acids? They're not the same. All right, ternary acids are different. The general rule for a ternary acid, if they have the same central atom, like, for example, I'm going to use a different example in a minute, but for example, H2SO4 versus H2SO3. You see what I'm saying? They have the same central atom, right? But they have a different number of oxygens. That's sulfur. What's the name of that guy? Sulfur, us, and this guy's sulfur. Okay. If they have the same central atom, the basic rule says that the acid strength is going to increase with the increasing oxidation number. Higher the oxidation number, that means the charge of the central atom. Oxidation number is just a charge. That's the better acid. So let's take a look at why it looks like it's. I'm going to show you up here what it looks like. Oops. Write that down, and then let me show you why that's the case. What you would do to figure that out by yourself. Okay? Because it's not about memorizing this. You don't memorize this, except for the rule. You do have to know the rule, obviously. It's more about being able to figure out the oxidation number. So, what do I mean by oxidation number? Remember, the total charge of that guy has to be 0, right? Do we know some of them in there? Do we know what H always is? +1, right? Do we know what O is? Look up there. -2. Those two guys almost never change. Almost never. There are some rare exceptions, which we're going to get later. What's the charge of chlorine then? If this guy's +1 and he's -2, what must the charge of chlorine be? Let's take a look. We got a 1 for hydrogen. My chlorine, I don't know. And my oxygen, I got 4 oxygens times -2 is -8. See what I did there? 4 times -2 is -8, right? And the whole thing has to equal 0. So what's chlorine's charge in this guy? +7. So he's a +7 up here. What's he going to be? Can we do this one a little bit easier here? What's he going to be now? +5. See it? Because 3 times -2 is a -6, right? And a +1. And the chlorine is the unknown, right? And the whole thing has to equal 0, right? So Cl would equal 6 - 1 or +5, right? What's this guy going to be? +3, right? And what's this guy going to be? +1. Got it? So you see why chlorine has the highest oxidation number. The rule says that's going to be the best acid. Okay? And finally, if they don't have the same central atom, okay, it's a different rule. The acid strength increases with increasing electronegativity, which is the opposite of the binary one. It's kind of confusing, I know. But it is the opposite of the binary acid. In binary acids, the weaker electronegativity meant you had a better acid. Here, the stronger electronegativity has the better acid. Because that electronegativity is being used to hold the polyatomic ion together. All right, so let's take a look. What would that be for this guy? See why HClO3 would be better than HBrO3, better than HiO3. If you don't, I will show you in a second. That's my last notes here. of these three guys, Cl, Br, and I, who has the highest electronegativity? Cl. So he would be the best. It's kind of the opposite as up here. Up here, all right, your acid strength got worse with the best electronegativity guy was HF, and he was the worst acid. Here, if I had HF in there, and it was a polyatomic ion, then it would be the best. Okay? All right. Yeah.
What if the different central atoms have different oxidation?
Yeah, then I wouldn't have a way to do it. In other words, I couldn't compare HClO4 with HBrO3. That wouldn't be fair. All right, because it has a different number of oxygens. It has to have the same central atom. If it has the same central atom, you go by oxidation number. If it has a different central atom, the other guys better be the same. Okay, so I wouldn't compare this, for example, to H2SO4. I can't do that. All right, and these are only general rules. If you wanted to know the real strength, you'd have to look them up in, like I said, in an appendix in the back of the book with actual constants.
So if you had like H2S or something,
H2S.
S would be the central.
Like,
H2SO.
O4 and H2SO3 and H2SO2. I could do that, you know, because they have the same central atom. I would use this rule here, okay? But I wouldn't compare H2SO4 to HClO3 or to HCl. I couldn't do that, okay, because that's going across them. And I'm sure there's a way to do it, but you don't have to be able to do those, okay? All right.